So my talk is gonna not a policy but engineering approach, and this is a low-cost technology that we're trying to see if we can improve transit operations. One is obviously called transit signal priority. The other is a measure of transit services, like how long do passengers are waiting, and then try to identify origin destination of their times, and how can we possibly deploy this into small, medium-sized cities that they may not have connected vehicle capabilities. It's costly and expensive. If you know about devices, it's about a couple of $1,000s, so it's not really affordable for small, medium cities. So I'm going to talk about transit signal priority first. If you think about transit signal priority, if you are at the 8 in the morning and nice lady from Tennessee State University presented about TSP, which is a very much interesting, and she basically reported the same idea, gives a huge benefit, but it often shows additional delay, not much, at the cross street, which you do not get the priority. Whole idea behind this is that you want to provide additional green time so that a bus is probably behind the schedule and carrying a lot of passengers and get through by having additional green time or borrowing green time from the cross street. So cross street is green, you truncate the green and add additional green time to the major street. Some of the problem is that sometimes you cannot really do overall entire cycle. You can only do beginning and ending of the green time. As I mentioned, extending green or truncating green from the other side. So why we are adding the vehicle to vehicle, vehicle to infrastructure, V2X technology here? Two things we are thinking is that now with the two-way communications, right now TSP, so-called, is only I'm coming, sending signal, and then controller side of traffic signal system accommodates that request and try to open it. And worst case happens is that extending green time for 5-10 seconds, bus could not make it, and that's really bad for entire intersection performance, not only for the cross street and also the approach. By having two-way communications, you have an option to cooperatively control. So bus is not gonna make it in current 5 second or even current green times. You can actually change that, even recommending higher speed within the range of acceptable speed boundary. So that's the idea we have it. And the key of this is that US DOT or ASHITO are really interested in this because this does not require a lot of market penetrations. Many studies show that if you want to have a benefit on connected vehicles, you need about 20 to 30% or higher vehicles equipped with it. And TSP happened to be only buses having that technology and having intersection having the device could work very well. So the logic I'm trying to show here is very simple. Now we can do cooperative control instead of just opening up green time for at the end of the green or truncating green on the other side. Let's do it for entire cycle by doing. So if you know this is a bus arrival range expected, and you are putting green time there, so you can make a green to go through whenever bus arrives at the intersection. And you need to have a good calculations, obviously. What about the queue ahead of my bus? And then other all the factors like bus dwell times and location of bus stops and everything. So we are basically creating an optimization problem that can solve this problem. If you anybody's interested, I can go over this for next 30 minutes, but I'm sure you're not. So basic idea is that trying to minimize the total delay, and we are consciously adding total person delay. So if a bus carries a more person and it has a higher weight for personal delay, so you can actually consider if it's a bus is late, but it's only carrying 2 people, then it's not worthy of doing adding person delay optimization. So we assume bus occupancy is known, and using that concept, we only allow bus to do this in case by doing this we'll minimize the person delay. So that's the whole idea with a whole bunch of constraints. We are comparing three different things, obviously. The base case without having TSP, and then conventional TSP, and then what we have proposed. And we use a bus delay. We want to know how bus can go faster than not having or conventional TSP. And then also the personal delay, including everyone in the car as well. So we actually had a real network of the intersection, but we could not really implement this in the real world because we don't have the technology yet. But we use actual volume data. We use actual timing plan data. So this is done by two things. One is what we call analytical way of solving this problem. So you know average arrival, you know the volume signal, you pretty much know everything, and you solve an analytical model to get the optimal or near optimal, depending on conditions, and you have the answer for it. And that's what we do in the model calculation of a device. If you were to implement this, this is how we get. But in real world, we have variabilities. Even you expect 10 cars per minute, it may get 12 or 8 cars. So we want to have that stochastic variability. So evaluation was actually done through the simulation model called the VISM. And again, the lady from the Tennessee state explained this in very detail, and we pretty much follow the same idea. Only difference is we use something called the COM interface, which allows a little bit more flexibility of changing things than the VAP that used. This is one picture showing why the proposed approach would work better. Is that if you look at this conditions, obviously you can tell this was a green time, this was the beginning of red. So if you are get stuck at the end of green, you wait that amount in this arrival time, and then as you're getting close to the end of red, your waiting time get reduced, and then you can get through without waiting. And if you are using without TSP is this, and do I have another one? Okay, this is the one. Actually, you are getting benefit of having conventional TSP. By extending green time to next 5 seconds or 10 seconds, you can reduce this amount of green time. But our approach will allow to reduce entire area by reallocating green time. So that's the advantage of having a proposed approach. That's a sort of a truncation of red. I'm not going to show this analytical model solution. It's just better, and a lot better because we know everything. But in reality, there's a lot of uncertainties. So with the simulation model, having VISM varying the arrival times and volume changes and all those behavior changes, and you can see that still bus delay is a different volume to capacity ratios. So we purposely tested out somewhat heavy and very congested conditions. And even these conditions, no TSP, conventional TSP, proposed TSP, you get the benefits of over even about smallest case, about 10%, and this amount of percentages. And even for the person delay, we get reasonably good performance for low viewership ratio, obviously, and even for the close to the congested conditions. So it kind of gives the idea of that this is going to work. The other one I want to show you is that this one is motivated by the city. Probably Kalamazoo is similar. I'm from the Charlottesville, Virginia, and they made a change in bus routes and moved the bus stops without doing survey of origin destination of those transit users. And we talked to them about the reasons, and they spent even $110,000 hiring consultant doing that kind of work. So even getting data from real people was not even possible. So we got motivated to help them out how to possibly getting transit performance data using technology. So we call it low-cost technology because it doesn't cost a lot of money. I'm going to show you this. This is something called tracking your device ID. It's called a MAC address. It's a unique ID, goes onto the chips that you use for your phone communications, like a Bluetooth. You use with your Bluetooth headset or Wi-Fi, you access to Wi-Fi hotspots. They get unique MAC addresses. And part of authentication process, you are sending your MAC address to the nearby area, and we are basically grabbing those information and try to use that information to match at the current bus stop to next bus stop. And then we know that device actually is went into the bus and moved with the bus to the next bus station. So that's the idea that we have used. And it's been widely used for travel time estimation on roadways. You basically read the MAC address, one location to the other, and you get the reasonably good travel time, and you post that into the providing guidance systems. In our case, we had two spots in our university campus, and using this low-cost device. If you know about this Raspberry Pi device, it's about $35 per piece. It's actually a computer, a small computer having 2 gigabytes of RAM, and you can use a USB thumb drive as a hard disk drive. It has a HDMI port and everything. So that's this device. And this is a Bluetooth reader. This small chip actually reads Bluetooth MAC addresses, about $7 to $8. And this is a Wi-Fi dangle. In case you don't have a Wi-Fi on your desktop computer and you want to use that as a laptop-like device, you put this into your computer and it becomes Wi-Fi capability. And this is a battery pack in case we don't have a power line there. So it's a less than $100 of device that we developed. And using Raspbian is a operational system just like Windows and Mac OS, commonly used for Raspberry Pi. We use the Python code to develop, and obviously the idea of having the cloud service. If we have Wi-Fi access to it and other devices, I'm going to talk about later, and we can actually send this information to cloud, and we get the data without having a large cost. So this is an interesting findings, and we tested with the Bluetooth first. We thought it's going to work. And the sample size was so small, and we realized that in the college, I don't know, how many of you are using iPhone? I'm not sure, but 70% or higher were using iPhones at the University of Virginia. And iPhone, to try to save a battery, they are not giving Bluetooth MAC addresses unless you are actively pairing. So you are trying to pair with your Bluetooth headset, or you're trying to pair with the other Bluetooth devices, then you send the Bluetooth MAC addresses. If not, you're not sending anything. So we're only getting the information from the non-iOS devices like Android phones. And even some people actually turn off their Bluetooth. Then you don't get it. Then we actually did a Wi-Fi reader. See the sample size. We did try the same time frame. We get this many Wi-Fi MAC addresses. And Wi-Fi reader has a different levels, and you can go up to a couple of 100 feet away. Device you can read. So that's a lot of data we're getting. So it's kind of interesting to have that. And I'm not going to spend much time on this one. This is a basic idea of utilizing this device and trying to show how it works. And we put into the departure time of the chemistry, arrival time of another building, and we actually had an actual device we have had, and then look at the actual travel times, and then estimate travel time based on Wi-Fi MAC addresses we are reading from one station. And then if that device, along with the people obviously, got onto the bus and moved to next station, stays there or got off, doesn't matter, then we can match two devices. And we can have a rough estimation of their duration of the devices being recognized by two Raspberry Pi devices. So that's going to give us an idea of travel time. It's reasonably good with the known device we have with the student carrying them, and get the idea of we can do this one. This slide is more complicated, but let me just skip this one because it's not worth it. Same idea, is just applying it. The key message I'm trying to give is that now we have a great algorithm for doing transit signal priority, and then ways of tracking devices for understanding waiting time at the bus stop or their original destinations by tracking these MAC addresses. What if we don't have money to pay for putting the DSRC, which is a dedicated short-range communication devices? City is not affordable to pay for those, and cars are not going to buy, and we cannot do anything. So we again try to look at the low-cost options. There's something called the LoRa technology, which is again using public bandwidth domain, and about less than $1,000. We even found one with the $500. It's a gateway you basically install this with the Wi-Fi access point. And this gateway can actually communicate couple of miles, long range. If you have a good line of sight, it could go 5 miles radius, and you can actually get anything with the gateway LoRa end node. It's about $50, goes into your Raspberry Pi, and this is basically a way of communicating it. If you don't understand this, think about walkie-talkie. You actually talk and get there and then communicate. But this is basically what they do. So basically having data, I'm sending through the end node to gateway on my LoRa technology and receives it. It goes into Wi-Fi hotspot and goes to Amazon cloud and any cloud services. The latency is about 1 or 2 seconds. So it's a reasonably good even for transit signal priority and also getting data from the bus stop waiting times or origin destinations. So just give us some ideas of this. So it could have different ranges of this. Bluetooth, you know, if you are going away from about 30 feet away and you lose communication of Bluetooth, especially you have a Bluetooth mouse and doesn't work very well. Wi-Fi could go up to 1,000. Zigbee is another 1,000. LoRa is up to 10 miles. So you can get reasonably good 5-mile radius of the communications. And this is a concept commonly used in smart cities applications because you don't have money to pay for a mesh network, which could be expensive, and also requires sometimes a data network, LTEs and 4Gs, which are expensive for end users, and try to replace that with the low latency and possibly up to 20,000 end node devices communicating with it. And that's what we are trying to. Oops, I had another slide here. Maybe it came out to 2 things. Anyway, these are students worked on this project, and we got funding from the Ford VA and also some collaborator from the DGIST. Happy to take any questions.